So the math that we just did for the Hertzian dipole showed us that the radiation resistance of the Hertzian dipole antenna is relatively small, since L is infinitesimally small, and really that limits the efficiency of the antenna. Remember that radiation resistance is really telling us how much power that antenna is going to be able to put out. So high radiation resistances are actually good. What we can see with antennas is that by making the radiating element longer, the radiation resistance can be increased, which will make a more efficient antenna, a better operating antenna. So when we increase the length of L beyond an infinitesimally small quantity, we call that a dipole antenna. And figure A here is representing a transmission line feeding a dipole antenna. The total length of this antenna is going to be L. So from here to here, the length of this antenna is L. Half of L is above the y-axis here, and half of it is below the y-axis here. And so we split that total length L into an L over 2 and an L over 2. So unlike previously where we assumed current distribution was constant along the Hertzian dipole, now there is an actual current distribution along the dipole element. Since the ends of the dipole are open circuits, current has to go to 0 here, and current has to go to 0 here. And the distribution of currents along the dipole is often approximated using a sinusoidal function right here. And that is that if we have a driving current, I of z comma t is equal to Is of z, so some sort of phasor current in along the length of the transmission line, times the cosine of omega t. So this is, well, what is the value of this current as we go along the transmission line? What is the distribution as we go along this dipole element? And it is approximated as Is of z is equal to, we've got I0 e to the j alpha times the sine of beta times L over 2 minus z, and that is the approximation for 0 is less than equal to z is less than equal to L over 2, so that's the approximation for this portion of the antenna element, or Is of z is equal to e to the j alpha sine of beta times L over 2 plus z, for minus L over 2 is less than or equal to z is less than or equal to 0. So all we're saying is that the distribution of currents in the dipole element can't be considered. If this is long enough, we can no longer make the approximation that current is constant. It has a spatial dependency as well as a temporal dependency. And we will define that using this piecewise linear function here. So this is the assumptions that are made for the dipole antenna. With this approximation, with this change to the current distributions, we get different magnetic field and electric field calculations. And the magnetic field strength at any point O away from a dipole antenna here is going to be given by H. The magnetic field strength at point O in its phasor form is going to be equal to J times I0 over 2 pi times e to the minus j beta r, all divided by r. And so that looks familiar, right? Now we're going to multiply that by cosine of beta times L over 2 times cosine of theta. So the cosine is taken of all of this stuff. Minus cosine of beta L over 2. we divide all of this by sine of theta, and this points in the a hat phi direction. A lot of times we will write the magnetic field as HOS is equal to its amplitude times the direction that it points in. That allows us to simply write the electric field as eta times the magnitude of HOS, and it will point in the a hat theta direction. This term, this bracket that gets multiplied by this magnitude multiplier here is often called the pattern function. We define the pattern function for an antenna. The pattern function for a dipole antenna is just everything that's in this brackets with the exception that we square it. And the squared term comes from the pattern function, doesn't refer to the magnetic field or to the electric field. It actually refers to the power. And we often will use pattern function to write the radiation intensity equation, which is just the cross product of these two. And since it's power, we know it's radiating away from the dipole element.